Today we're diving into a paper that explores a new approach to the k-nearest neighbor, KKNN classifier. This paper, Adaptive K-nearest neighbor classifier based on the local estimation of the shape operator, proposes a method to dynamically adjust the neighborhood size based on the local curvature of the data. What's the main challenge that this paper addresses?
The main challenge is the sensitivity of the KNN classifier to the parameter k, which determines the number of nearest neighbors considered for classification. Choosing the right A value is crucial for balancing bias and variance, and it can be difficult to find a single value that works well across the entire dataset.
So how does this paper propose to address this challenge?
The paper introduces a new adaptive KN classifier called KKNN, which uses the local curvature of the data to dynamically adjust the neighborhood size for each sample. The idea is that points with high curvature, where the data is bending sharply, should have smaller neighborhoods, while points with low curvature, where the data is relatively flat, should have larger neighborhoods.
That's an interesting approach. Can you explain how the local curvature is estimated?
The paper proposes a method to estimate the local curvature using the shape operator, which is a mathematical concept from differential geometry. The shape operator is a linear transformation that captures the curvature of a surface at a point. The paper approximates the shape operator using the local covariance matrix and the local Hessian matrix, which are computed from the neighborhood of each sample.
So the shape operator is used to estimate the curvature, and then this curvature information is used to adjust the neighborhood size. Can you elaborate on how this adjustment is done?
The KKNN classifier first builds a k-nearest neighbor graph, KNNG, using a fixed value of k, typically log 2n, where n is the number of samples. Then, the curvature of each sample is estimated using the shape operator method. These curvatures are then quantized into 10 different scores, representing different levels of curvature.
And how are these scores used to adjust the neighborhood size?
The scores are used to prune edges in the KNNG. For example, if a sample has a curvature score of 4, then the edges connecting it to its 4 farthest neighbors are removed, effectively reducing its neighborhood size. This pruning process is done adaptively for each sample based on its curvature score.
So the KKNN classifier essentially creates a variable size neighborhood for each sample based on the local curvature. What are the potential benefits of this approach?
The paper argues that this approach can improve the performance of the KN classifier in several ways. First, it can help to avoid overfitting and underfitting by adapting the neighborhood size to the local characteristics of the data. Second, it can lead to smoother decision boundaries in regions of low density and more precise boundaries in regions of high density. Third, it can improve robustness to noise and outliers by isolating high curvature points, which are often associated with outliers.
That's a compelling set of potential benefits. What are the main results of the paper?
The paper conducted extensive experiments on 30 real-world datasets, comparing the performance of the KKM classifier to the regular KNN and another adaptive KN algorithm. The results showed that the AKN classifier consistently outperformed both the regular KNN and the competing adaptive KNN algorithm, particularly when the training dataset was small.
So the AKN classifier seems to be particularly effective when dealing with limited training data. Can you elaborate on why this might be the case?
The paper suggests that the AKN classifier is able to learn more discriminant decision functions with less data because it adapts the neighborhood size to the local curvature of the data. This allows it to capture more subtle patterns and relationships in the data, even when the number of training samples is limited.
That's an interesting observation. Are there any limitations to the KNN classifier?
One limitation is the computational cost. The curvature estimation method used in the KNN classifier is more computationally expensive than the regular KNN algorithm. This could be a concern for large data sets or real-time applications.
So there's a trade-off between computational cost and performance. What are the potential future directions for this research?
The paper suggests several potential future directions. One is to further investigate the theoretical properties of curvature adaptive classifiers, such as their convergence properties and performance bounds. Another is to explore applications of the KNN classifier in other domains, such as image processing and dimensionality reduction.
It's interesting to think about how this approach could be applied to other areas of machine learning. Can you elaborate on the potential applications in image processing?
In image processing, the KKNN classifier could be used to identify objects or features in images based on their local curvature. For example, it could be used to detect edges or corners in images, which are often characterized by high curvature.
That's a good example. So the TKN classifier has the potential to be a valuable tool for a variety of machine learning tasks. Can you summarize the key contributions of this paper?
The paper introduces a new adaptive KNN classifier called KKNN, which uses the local curvature of the data to dynamically adjust the neighborhood size for each sample. The paper demonstrates that this approach can improve the performance of the KN classifier, particularly when dealing with limited training data. It also highlights the potential of curvature-based methods for other machine learning tasks.
Thank you for breaking down this interesting research. It's clear that the AKNN classifier offers a promising approach to improving the performance of the KNN algorithm. It'll be interesting to see how this research develops in the future.